Hi everyone, we are group 2 from Math 5671. My name is Wen Yang and I'm a graduate student in actual science major. And his name is Yele Yuan and his name is Yingfa Xie. They are both graduate students in applied financial math. And we are going to present our final project. Okay.
Today we will talk about Australian credit card approval. As we know, commercial banks receive a lot of applications for credit cards. Many of them get rejected for many reasons, like high loan balances, low income levels, or too many inquiries on their report. Manually analyzing this application is mandated, error-prone, and time-consuming. So this project is trying to find a way to build a model that can automatically analyze those credit card applications. This project is to create a model to classify credit card applications. We need to predict the result that applicants will pass the credit card applications or not. The digital number 1 stands the applicant successfully passes the credit card application process, and 0 means the applicant fails. We can see from the below screenshot, the data provided contains 6 numerical attributes and 8 categorical attributes. All attributes, names, and values have been changed to meaningless symbols to protect confidentiality of the data. This dataset is good for practice purposes with continuous as well as nominal attributes. There are also a few missing values. In order to examine a prior's application, we need to use the dataset to train the model. Firstly, we need to transform data type to fit the built-in models. Secondly, we need to find appropriate methods to train our models. Since the dataset represents the feature of a prior's background information, a prior will be denied by some common reasons, such as low credit score. Therefore, the linear regression model might not be suitable for this problem. So we decided to choose neural network or classification methods to process data and make predictions. Because classifiers may help us to classify the applicant's information. Finally, we can use the trained model to make predictions. The first step, transform data type. In this part, firstly, we import Spark to read and process the data. Next, we loaded the dataset. We loaded the features into a data frame called features. And we use the same code to load labels into data frames again, called labels. The data frame's features and labels are shown below. As you can see, the first column is not belonging to our 14 attributes, so we will drop this column. We need to use the vector as assembler to combine features columns into a single vector column in order to train machine learning models like logistic regression and decision tree. We created a function named trans to transfer the format of the data. Since vector assembler accepts all numeric types, Boolean type, and vector type, and the data in our data frame are string type, we need to transform each feature into double type. Then we used a vector assembler to combine feature columns into a single vector column.
Then we used the function we created to transform the data type. In order to train machine learning models, we need to combine the two data frames. So we used the monotonically increasing ID to create a new column in both data frames. For example, data frame label will have a new column with an increasing serial column. Next, we use join to combine the two data frames, and we dropped the useless columns and modified the column name of the results into label. Now we have two columns. The first column is the combination of all features. The second column is the label, aka the results of application. In this part, we tried two models and we put the models together in step 2 for presentation. In practice, we better run each model and their following steps before we trained another model. The first model is Multiplier Perception Classifier, aka MLPC. It is a classifier based on the feed-forward artificial neural network. It consists of at least 3 layers of nodes, an input layer, an hidden layer, and an output layer. Each layer is fully connected to the next layer in the network. Nodes in the input layer represents the input data. In this project, it's the dataset we read from the CSV file. We split the dataset into 2 subsets, which are train sets and test sets. The train datasets contains 70% of the whole total dataset, and the test dataset contains 30% of the total dataset. We set the layers as 14:4:2. The question of how many hidden layers and how many hidden nodes are always comes up in any classification task using neural networks, and there is a ton of literature on it, but there has been no exact solution. Among the empirically derived rules, the most commonly relied on is that the optimal size of hidden layer is usually between the size of input and the size of output layers. And some people suggest the size of hidden layer in general should equals the logarithm of n to the base 2. In this case, n equals 14, which is the size of input layer, or square root of n times L, and L is the size of output layer, or n plus L divided by 2. In this project, we set the structure as one input layer, one hidden layer, and one output layer, and we choose 4 as the size of hidden layer. Then set the other parameters of the model as default. We used train sets to train our model, used the test dataset to test the trained model. The accuracy is about 75% to 85%.
Alternatively, we also try to use random forest classifier to check if we can get the better results. Random forests are ensemble learning methods for classification, regression, and other tasks that operates by constructing a multitude of decision trees at training time and outputting the class that is the mode of the classification or mean prediction of the individual trees. Initially, we use string indexer to add metadata to the label column. If the data in label column were strings, this would transform the labels to the numeric. We coded this for general uses, and we used vector indexer to automatically identify categorical features and then index them. Use 2 features transforms to prepare the data. Indexing categorical features allows random forest classifier to treat categorical features appropriately. Hence, we might improve the performance. We set the max categories 14 because A5 has 14 distinct values. After processing by these two functions, the original values of A1, A4, A5, A6, A8, A9, A11, A12 are converted to category indices, while A2, A3, A7, A10, A13, and A14 are considered as continuous. Then we could train a random forest model using indexed label and index features. Similar to string indexer, index to string maps a column of label label index back to a column containing the original labels as strings. We retrieve the original labels from the column of predicted index with index to string. Then the most critical step in this part, use pipeline to chain these three procedures from indexer to random forest to label converter. And we fitted the data frame train and use data frame to test the model. The accuracy is about 80 to 85%. In this part, we use the trained model to process test data and return the results. Firstly, we imported the data from testFeature.csv. We used the prior defined function transdef to transform the data type. Then we used the model transform to fit the test data. The results are showing below. We selected the results of the predicted label and we modified the column name and added a serial column into the data frame. Step 3 using random forest is basically the same with MLPC except one little difference. Predicted results is stored in column prediction when using MLPC and column predicted label when using random forest classifier. As you can see in this project, the RF model's performance is better than MLPC, but that doesn't mean RF is generally better than MLPC. Thanks for listening.